30. Okay.
Yeah, great.
Have fun.
Will do.
A bunch of people are still in the cafeteria, so should I pull them in?
And there was a little bit of feedback. Can everyone hear me from here? Can you hear? Is this the? You're good? Thank you.
Most of it is for online. Lapel mic, if you want to walk away from this. Regardless.
No.
Oh, always.
No. I'm good. Oh, yes.
Yeah.
Oh, okay,
yeah.
great.
Otherwise, I'm sorry to say, but our
it's fine.
people are here.
Oh, no, that's totally fine. That is totally fine.
Put this down.
Oh.
And usually picked up the wrong one.
Oh, boy. Then I'm going to move these up. There was a lot of feedback yesterday, and I couldn't figure out what was going on there. So we'll just do that.
And it actually was not related to those specifically. Which mics they are yet.
Ooh. You have or have not? Not. Perfect. That's fine.
And slide advancer and laser pointer if you want.
Easy, breezy. Yeah, great, thank you.
And then let's start.
Oh, and I bought this little cute bell that Amazon probably paid $5 to order this $4 bell. We need to get people's attention.
Let's start.
That just looked like a god.
I know. I need to get my glasses.
It's a lot going on. Morning. Do you want to just shave off 2 minutes? What's the time here?
Yesterday we were finishing early, so we can start 10 minutes late.
Oh,
That's fine.
that feels.
So you get
You nail it. Okay. Just like to manage which clip of where we can digress and where we can be like, we don't need this.
Okay, ready? All right, everyone, welcome back for day 2 of the exciting workshop. As you're coming in and settling down, I was asked to remind you about the Slack channel for the workshop. You're welcome to be posting questions there, making comments. There'll be a prize for best pun by the end of the day. I was just told, actually, I just made that up right now. And speakers should also be checking that channel at some point after their talk to see if there are unanswered questions. Any other announcements? We good? Okay, so with that, we have 4 presentations before the first break of the day. First one will be by Shannon Curry, and it's observational strategies for atmospheric escape in the solar system. Take it away, Shannon.
Okay, thank you guys. It's good to see everyone this morning. So I wanted to just get started with, again, one of the reasons, especially in this solar system, why we've studied planetary escape. Obviously, everyone here in this room, I'm preaching to the choir, but nonetheless, you know, especially since so much of the planetary community are geologists, we do like to remind everyone that atmospheric escape is really key for understanding the presence of liquid water, right? So this is Mars, or I should say one of these is Mars. Does anyone know which? Okay, so what you're actually looking at, that is the Grand Canyon and that is the Native Vallis. And so in particular at places like Mars and then even Venus, we like to remind everyone that for water to be in stable liquid form, you have to have enough atmospheric pressure pushing down on it. So I happen to be a total atmospheres person, but if you do like getting below 50 kilometers, then this is something of interest to you too, because again, for water or really anything in liquid form to exist in a large stable body, you need that atmospheric pressure. And we know that early on in Mars's history, as the atmosphere started eroding away, that atmospheric pressure wasn't high enough, right? And then that water started evaporating, and then the rest is what we all go to conferences and speculate over. So, okay, let's go a little bit bigger in thinking about atmospheric escape in our solar system. So what you're looking at temperature, and then you're looking at escape velocity in this chart here. And so what you'll see is looking at the temperature of each of these bodies, you can then look at what the escape velocity is, and that's also based on their gravity, right? So when we start to think about how things escape a planet or a moon, what you're thinking about is how the gravity, right? Because these the outer planets are colder, but they are massive. So that escape velocity is enormous, right? And then you have some of the smaller planets in here, right? And then of course you've got Venus, that's pretty toasty. And then on each of these colored lines, you're looking at different, you're looking at, you know, carbon dioxide, oxygen, helium, hydrogen, et cetera. So these are going to be different atmospheric constituents. And so if you're particularly interested in one of these, you can find which atmospheric constituent you're most interested in, which planet. You can more or less start to map, okay, so is there a possibility for escape? So we'll just use a quick example. So like at Venus, you'll notice that here oxygen and nitrogen are below it. That means that oxygen and nitrogen are not going to escape thermally there. So things like photochemical escape aren't really going to work as well. So this is important as we start to go forward and think about exoplanetary systems. And we can start to say, okay, so if a planet is, you know, more massive but really hot, what does that mean? Or if a planet is really small but cold, what does that mean? So trying to visualize where we are in this space, again, temperature and the mass of the planet are really, really, really important when we think about that escape velocity, because, right, this is sort of the premise of a big piece of atmospheric escape. Okay, so when we think about atmospheres in our solar system, today we're gonna talk a lot about, in particular, Venus, Earth, and Mars. Because as you can see on this chart over here, with the outer planets, there are a lot of things that really can't escape. You can get atmospheric escape there, and we'll talk about those mechanisms, but the majority of the physics we know about atmospheric escape exists at Mars, Earth, and Venus, right? Now here's the interesting part. You might say, okay, so now that if you know the mass and the temperature, you should be able to write a simple equation. Not quite true, because I know that there are folks in this room that are very deeply invested in how we got those atmospheres in the first place. So at Mars, we're looking at, I think I have that, oh, no, we don't. So at Mars, we're looking at like 0.7 millibars. 0.7 millibars. At Earth, in terms of the surface pressure, we're looking at Earth is 1 bar, Mars is 7 millibars, and then Venus is about 90 bars. So that's a huge difference, and that's not entirely explained just simply by, you know, the mass of the planet and its temperature. A lot of that has to do with outgassing. So we won't be going into that today, but I do want to point out that this is outgassing and how these atmospheres formed is really, really important. And I would also point out the presence of a magnetic field is also important, although not yet well constrained. So at Mars, we don't have a global dipole magnetic field. We have all of these little crustal fields in the southern hemisphere. At Earth, we have this really beautiful dipole magnetic field. We'll look at that a lot today. And then at Venus, as far as we currently know, it is completely unmagnetized. So these are all these are all ingredients in trying to understand the atmospheres that we see in the present day. In terms of the outer planets, right, so this is where when we start to think about atmospheric escape, there's a lot to talk about in terms of atmospheric dynamics of these planets, but that's not for today's talk. So when we start to think about escape from these planets, we're going to be really looking at like hydrogen, helium, and then maybe some very light hydrocarbons. But that said, these are really, really exotic places to explore. But some of those heavier constituents, we don't really think of those as escaping. So I think most of you know this, but I did want to do a quick review on the solar wind, right? So the solar wind is the stream of charged particles, namely protons, electrons, and alphas. It's streaming from the solar corona, and as the sun rotates, it rotates with it, right? And so this is called the Parker spiral. And so you get these stream of particles. Trapped within it are these lines called a magnetic field. So this is the sun's magnetic field. We call that now the interplanetary magnetic field, as it gets frozen into all of those particles and then carried out and propagates through the solar system. This is incredibly important because so much of what we know about atmospheric escape is driven by this very interaction. So when we start to think in particular about like the terrestrial bodies, this is more or less what an unmagnetized body looks on the left, and then a magnetized body here on the right, what those are going to look like, especially as they interact with the solar wind and the IMF, or that interplanetary magnetic field. A little bit more of a technical approach. So what's happening is you form a shock, and all of these atmospheres, if you have an actual atmosphere where there's an exobase and you go from a collisional to non-collisional regime, you're going to have an ionosphere, right? That's when that EV radiation comes in, ionizes a lot of those particles, and you create this conducting ionosphere. So the ionosphere here, the neutral atmosphere and the ionosphere serves as a reservoir for escape in these weakly magnetized planets. In a magnetized planet, it's going to be a little different, and we'll talk more about that. But a lot of the particles, at least in the systems that we know it, really we're going to be focusing on how these magnetic field lines start to connect, and then how particles can get charged, become ions, and then they can follow those actually in and outside of this system. So Park showed this yesterday. This is a figure that our Nexus team did a couple of years ago. It's aggressive, I won't lie. There's a lot going on here. We're not completely going to unpack it, but I do think it serves an important purpose when we start to think about, more or less, what are we looking at? This is Earth, but really this is going to be a magnetized planet with a dipole field. And you can see things like a polar wind, charge exchange, or genes escape and outflows. I've tried to list a lot of the main processes here. In terms of here we have a comet, right? A comet is sort of like the original way we know about atmospheric escape. It's just sort of that bullet-like object going through the solar system. You can have charge exchange and hydrodynamic escape. Here, right, this is Venus. And so you can see things like sputtering and ion escape. But then over here, you'll notice you get photochemistry at Mars, as well as ion escape. We'll talk a little bit about why photochemistry, especially for heavies, is only listed down here at Mars. This is actually from that same paper in 2019. The reviewers liked this visually, but felt physically overwhelmed. So we wanted to try and again, just lower the temperature a little. There's my pun. And here's the stellar wind. And then this is going to be that the stellar wind and the stellar EUV flux, right? And so even if you're not a plasma person, you can sort of follow. This is like a pick your own adventure, and you can kind of follow this chain. So very briefly, we can start over here with unmagnetized planets. When you have a stellar wind, you can get things like charge exchange, pickup ions, and sputtering. We're going to talk about all of these. And then this is what can be happening at both. You can get major ion escape, genes escape, potentially a photochemical escape, and then thermal hydrodynamic escape. As a magnetized planet, you're going to get things like ionospheric outflow and charge exchange. And those are going to be namely driven by the stellar EV flux, but also in terms of some of those winds. So when I look at this, if I was going to give a pop quiz, I wouldn't expect everyone to be able to like draw these out. So we're going to do that here. Genes escape. Lighter elements, this is the loss of particles from the energetic tail of the distribution. Photochemical escape, right? That's when a photon comes in, breaks up a molecule, and then it can be, you can have dissociative recombination, right? And so here, well, we'll just go into it. So for genes escape, I like to think of it as here as a temperature distribution. On the cold end, they're just doing their own thing. But on the hot end, you can actually have something that just naturally escapes from the tail distribution. With photochemical escape, and these are highly technical drawings, so just take them with a grain of salt, but you're going to get, right, a photon comes in, breaks up that molecule, and then it escapes like so. Okay, hydrodynamic escape, this one's really this is one of my better animations. Here is where lots of photons come in, and then the lighter elements drag out some of the heavier elements, known as viscous escape. Or it's viscous drag, I should say, on it. Okay, ion escape. This is where neutrals are going to get ionized by that incoming solar wind radiation. And then all of a sudden, the magnetic fields that they couldn't see before can actually get sensed, and they can get carried away. Ion outflow in the polar wind, that can happen the same way. You've got just neutral atmosphere, it gets ionized by radiation, and then all of a sudden it sees a magnetic field, but namely in a different place. So here, right, you've got a photon, it makes an ion, and all of a sudden this ion can actually see the magnetic field, and now it can get away. And with the polar outflow, it's going to look a little bit more like this, right? So now you have that same ion, and it can go out through what we call an open magnetic field line in the cusp regions of this magnetized body. So here's the difference when we sometimes talk about like pickup ion escape versus ion outflow. That's now what the difference is. So finally, last but not least, sputtering. Sputtering is ion driven. So what happens here is ions come and basically like do a cannonball into the atmosphere and splash out neutrals. So here what you're going to see is you've got your ion, you've got this magnetic field, it actually crashes into the atmosphere, and then it splashes out a particle. So now you know your atmospheric escape processes, all of them. So if you ever want to draw these out, this is the most basic way to visualize it, but I do like to visualize it because all of them result in some sort of atom or molecule leaving the system, but it's useful to understand some of the distinctions. This is probably like 30 hulls at AGU, and so we just wanted to distill it for the sake of this talk. Okay, so we're back to this beauty. We're going to start with unmagnetized planets. Okay, so here are the processes that can actually happen in unmagnetized planets, right? So because when we think about sort of what can happen where, now that you know what these processes are, it's important to understand what kind of bodies they can happen at. So again, this is Venus, this is Mars. Again, we're going to come back to our escape energy. So this here, this is hydrogen, oxygen, O2, and then again, you can see that for Venus and for Mars. The thing I want to note in particular, when we go into these four processes, we'll start with photochemical escape, is that let's see, I switched these. This is Venus, this is Mars. It's like, that doesn't look right. So just pretend these are switched. At Venus, you're not gonna have oxygen and O2 escape, but at Mars, that escape velocity actually works. So let's just quickly unpack photochemical escape a little bit more. Dissociative recombination, right, is when this O2 plus ion gains an electron and becomes a neutral again, albeit it's now excited in one of these three states. And so one of the things to note is that when this happens, all of these different, basically they're all of these like effectively like branching ratios that here you can see they don't all happen equally, and they don't always happen with the same kind of energy. So for the escaping source, you can see they get up to 7 EV about 20% of the time when they make this jump, right? When they get up to this, like all the way up. But you can see that that's not typically about 45% of the time, right? You're going to actually get up to 5 eV when this photochemical reaction takes place. But you're going to have a bound population as well. So this is its own field of photochemistry, but it's just worth noting that all of this is going to be dependent on that incoming EV radiation, the density of the electrons, so how many electrons even exist in that well for this reaction to take place, and then certainly oxygen being one of the more reactive constituents in an atmosphere. This is one of the, this kind of dissociative recombination is going to be one of the more effective ones. So again, Venus, Mars. So photochemistry, I should also note, is actually photochemical escape is the ¡1 way the atmosphere escapes at Mars right now. At Venus, it doesn't happen because that oxygen is too heavy. Oh, that oxygen here is too heavy. So at Venus, something like this can't happen. And one of the really just small things, I'm not just plugging Mars because of my own background, but I will say Mars is a really cool laboratory because it's small, and that means we actually get to study this in a way we actually get to see photochemical escape in action at a planet we once thought was habitable. If it was larger, we wouldn't be able to study this. And granted, if it was larger, who knows what it would look like. But it's a really, really cool laboratory to understand all of these escape processes. Okay, genes escape, right? You're looking at the tail end of this velocity distribution. This man, who's looking down, will tell you about it in the next talk. So I'm not going to go into it here. But again, that's where we're going to be at the tail end of that distribution. So tune in. This will be very, very exciting. But I was going to, either way, you can get genes escape from both smaller and our larger terrestrial bodies, not except Neptune. But okay, ion escape. And this is where we're going to go with unmagnetized planets. We're still in unmagnetized planets right now. So here, this is Venus. This is a diagram we did a while ago. Basically, what you're getting is, there are like lots of kinds also of sort of like bulk ion escape. We won't go into all the granular ways that they can escape, but again, the main point is that the upper atmosphere gets ionized and then it senses magnetic fields, and in a number of ways can get slingshot or just simply accelerated away through the system. One of the really cool things here, this is the main way the heavy elements or the heavy atmospheric constituents in Venus's atmosphere escape. Because photochemistry isn't effectively taking place, like oxygen, because at Venus, oxygen cannot really escape photochemically. This is the only way to get oxygen out of the Venusian atmosphere. And so ion escape becomes a really important player when we start to think about, all of these things and the cumulative, the sources and sinks. I should point out, again, this is really important because it depends on the solar wind. And you guys remember sputtering. So as these particles, right, they're gyrating around a magnetic field, they can escape through the system, but they can also crash back in like we just saw. Sputtering, and I'm going to take a small detour here because this was the last, I'm going to say we've observed hydrodynamic escape, granted not in this solar system, but outside. And I would say, I feel comfortable saying that. But sputtering was the only thing left on this list of processes we've talked about that as of like 2 years ago, we had never actually observed, and it was still only modeled. We'd never at any atmospheric body seen atmospheric sputtering. Why do we get so bent out of shape about it? Because these are what the lighter ions do. But this is more or less what the heavy ions do. They splash everything out of the system. So this is one of the ways we actually think that sputtering actually 3 to 4 billion years ago would have been the most important atmospheric escape process at Mars, and could very well likely have been the major player in removing a lot of that atmosphere. Just a small detour. How do we know it actually escaped? So from isotopes. Okay, argon 38 to 36. If you're an isotopes person, this is one of the ways. Right now, we don't really have the resolution to do this outside our solar system, but isotopes are really, really, really important in being able to understand the history of an atmosphere. So for example, in this study, argon 38 to 36 just means that at the top of the atmosphere, the lighter species were picked off before the heavier ones. This can't happen with hydrodynamic escape because hydrodynamic escape is like a bulldozer. It's just going to take the whole top of the atmosphere off. But to get just the 38 to 36, that's a very small difference. That's like the portion of a scale height, right? So what's happening here is that you're actually you have to have something that's just operating at the top of the atmosphere and it's not going all the way down. And so for this, when we found this ratio, so this was Bruce Gkouvelis back in 2017, we started realizing sputtering must be taking place. There is nothing else, because argon is an inert noble gas. Nothing else can remove it from the atmosphere. And just two more things on this because it's never been observed before, so we're really excited about this study. When you think about precipitation, here's the solar wind, right? There's this magnetic field. We don't have to go into plasma today. That's a cross product, but that's the electric field that accelerates particles into the atmosphere. So really what's happening is what we wanted to do was look for argon where these cannonballs were all taking place. And that was what we did on MAVEN at Mars. And so what we did was we looked in the area, basically whenever you have this electric field pointing somewhere, we would look in that same area for argon. Because we know argon doesn't ionize easily, and we also know that argon is not going to sense a magnetic field. So if you see more argon where this is happening, then there must be sputtering. And so what we did here, really quickly, we looked at all the constituents. This is the total density of argon. This is your altitude and your density. And then you can actually use models. So for all the modelers, without you, none of us would be able to test these cool things in space, so thank you. So this is the thermal, the dissociative recombination, and then here, really charge exchange, and this is the sputtered component. So this only happens at high altitudes. You can see here at lower altitudes, like below 360, we were never seeing this. So it took us about 10 years of data to do this. And this is one of those cool experiments where we start to think about sputtering as an atmospheric escape process is really important because that applies everywhere. But since no one had observed it, it takes an asset like MAVEN 10 years of data to actually find this. We had to look on the day side and the night side. Once we finally did that, this is all of our solar wind data. This is where the spacecraft was on the day side and the night side because you have to look on both sides. And this is all of our argon data. And so what we found was we looked on, there we go. We looked like at high altitudes and we looked at low altitudes. And then we just took the ratio of, okay, if you take all the argon up here and then you take all the argon up here and you divide it, at the lower altitudes, we didn't find anything. But at the higher altitudes, that ratio was incredibly high. And you really can't get inert, noble argon, right, reacting to a magnetic field in any other way. So this was one of our really, really exciting atmospheric escape process discoveries because we just haven't been able to see, to actually observe this anywhere else. And I would point out, I talk a lot about MAVEN, but we don't have something like this at Earth. We've never had a dedicated atmospheric escape mission at Earth, which is sort of absurd, but I would point out we actually know more about atmospheric escape at Mars and really Venus than we do about our own planet. This is just a final, let's show you a little movie here. During a solar storm, we are exactly, here's Mars, so I say we loosely, we are in the right place at the right time, and you can see this is the pressure of the storm, this is the electric field it generated, and here's that enhancement in argon. And so this was just a really clean example of exactly what you would see. They all line up right around that same time, so it got lofted into the atmosphere. Okay. So let's go on. So that was an unmagnetized body. We are going to get to observations and how you would do it. So let's go to magnetized bodies. I'm just going to show you this because if you're not familiar with the magnetic reconnection cycle, this may not be, words really don't do it justice. So you're going to get magnetic reconnection on the day side from the IMF coming in. And as you get magnetic reconnection, it puts pressure on the tail. And as the tail starts to narrow, you're going to see more magnetic reconnection. And here at Earth, this is actually what causes a lot of that ion fountain escape, right? It's when it connects on the tail, not the day side, but the tail. And this is how the aurora forms. So really, really obviously beautiful byproduct, but namely, this is where you're going to get these kinds of constituents escaping at a magnetized planet. So it looks totally different. And that's why we like to distinguish when we talk about ions just escaping from the tail, like you saw on Venus, versus this kind of a process. They are totally different things, and they have really different escape rates. So especially when you start to think about like how much atmosphere was removed over time, this is really a big one. So I will just briefly go into the sort of, even within this, there are still separate kinds of atmospheric escape, or ion escape, I should say. You get a classic, it's called a polar wind, and this is where you're going to have lighter species like hydrogen and helium on what we're going to call them like open field lines here, and they can actually and they can be pulled out. And so something similar like this can happen at Venus. An ion fountain is actually when you're going to get heavier, like oxygen, things like O2. That should actually, I think, say O2 over here. Those can all escape. Same thing on the open field lines. And then you have something called an auroral wind. That's going to be on a closed field line. It's going to be like an actual just like this right here is a closed field line, where this is going to be an open field line. And so these are just distinctions made within the magnetized in particularly the Earth magnetosphere community. But all of these are ways that ions can escape. But you'll notice they have to be in ion form. So, all right. So did anybody here study Earth's magnetosphere? I was hoping nobody would raise. I'm joking, because I'm not going to go over this chart because I don't understand it. But I was an author on the paper, and I promised I would show it because it's a very complicated system, which I concur with. So if we all concur that this is very complicated, we're going to move on. But the point is that there's a lot of inward and outward flow in Earth's magnetosphere, and it's taken very seriously by many folks, one, and many others not in this room. So we are going to go on. Okay, but let's go to observables, because that's the fun one. So when we think about, okay, so I've told you about, we've physically now looked at and described these processes. We figured out which types of planets they occur at. So let's think about observables, right? Because a lot of what we want to do here in this solar system, we want to take and see if we can do elsewhere. So things like genes and photochemical escape. Ultraviolet is the way to go, right? When we start to think about an escaping atmosphere. So ultraviolet, if you have an opportunity to launch anything, I encourage you to use to get some kind of UV on there. Right, and so spectrographs and spectrometers, we have two experts in the audience, Kevin and Evgenia, who can tell you all more about this kind of instrumentation. But this is a really wonderful way to observe genes and photochemical escape. And so this is just a small smattering of the papers, but like, for example, like Maven has done an enormous body of work on this, and certainly within the exoplanet field as well. So John Clark, who we also have in the audience, this is actually Hubble's UV. And so this is another great way. Hubble was actually able to look at Mars, and they did a really, really incredible paper in Science a couple of years ago, looking at these measurements and trying to also understand like the D to H ratio. This is, again, the UV is an incredible way to try and look, to try and understand genes and photochemical escape. With sputtering, this is where you're going to, for photochemical and sputtering, if you can use a mass spectrometer, that's great. Here we are in situ, so if people just want to move on, that's fine, because I realize that works in this solar system. But obviously, for a large portion of this audience, that's not really applicable. But I would be remiss if I didn't at least say that this is one of the ways we know about a lot of these processes. And it's so important because, again, what we learn in our own natural laboratory can now be applied elsewhere. Okay, so now we get to ions, also in situ, but it informs the system and it will link to something else. So this is where we can get like really, here at Earth, this is a really nice study by Hull et al. We've had literally dozens of missions at Earth looking, that have observed pieces of escape. Nothing has been dedicated to understanding all of atmospheric escape at Earth, but we've had plenty of observations of that ion outflow, so we know it happens. And then certainly we've also had many missions at Mars and Venus that do the same thing and look at this really incredible tail. But again, these are in situ. So that brings me to my next piece, which is a little bit more relevant to you. This is the solar cycle, and these are all of the missions we've observed and looked at atmospheric escape rates at Mars and Venus. And so this is really important because we now have many solar cycles to understand how atmospheric escape has changed. The difference in escape rates over a solar cycle can be an order of magnitude. So that's pretty big. So this brings me to a point I cannot stress enough, that the stellar host, we now know, if I've not driven this in enough, that ion escape is one of the most important players when we start to think about atmospheric escape at large. Yet, we're not bringing an electrostatic analyzer, really outside, right, our own heliopause. So what can we do? We can start to think about the host stars and understanding, what we know in this solar system and applying that to other stellar systems. So we know that our sun, right, as it began to lose angular momentum and spin down, our sun, despite the faint young sun paradox, faint does not mean not active. We believe that our early sun was much, much, much more active. If you actually do some of the math back in time, we couldn't have gotten as much atmospheric escape at Mars as we see without a more active sun, because it has like these solar storms, coronal mass ejections, these stream interaction regions, flares. There's all this incredible solar activity that takes place that, at least at Mars, we don't think that a lot of that atmospheric escape could have actually occurred without a more active younger sun. So this is just an example. It's really beautiful. Here's Mars, here's Venus, here's Earth. It's criminal that we didn't have an acid at Venus, but that's besides the point. So this is a really nice example. This is one of the biggest solar storms we ever observed back in 2017. And this is just a plot here. This is just the solar zenith angle, meaning day side, night side. And then here, this is the flux. During this storm, we saw, again, actually like orders of magnitude more atmospheric escape. There are these red dots, and the blue dots are just the nominal atmospheric escape we see. So I just like to analogize solar storms come through and due to an atmosphere, if you're thinking about like a coastline and there's just sort of water lapping at the shore, that's just nominal erosion. But when a hurricane comes through, that's what some of these solar storms do in terms of eroding the atmosphere away. So there's just the bonus here is that while this is not an overt atmospheric escape observation, understanding the host star is so important, and actually making observations. And plenty of folks in this room have actually helped lead major studies on understanding the particle environment. There's some very cool studies on could you use, like dimming, and to see if there's a coronal mass ejection or something like that, right? Because that active region will dim as it erupts because it's more magnetically active. And so there are all these very cool ways to start to think about how we understand the particle environment around another star. That's an area that I think is, for me, that's the next most important step when we start to think about atmospheric escape in other systems. So you can do that, luckily, in a number of ways, like an AIA type instrument that's on Solar Dynamics Observatory, but you don't have to actually leave our solar system to do that. We've covered a lot today. This is sort of an aggressive chart too, but Mars, Venus, Earth, Neptune, Jupiter, I'm including them because they're useful. In green, that's the dominant, what I believe is the dominant escape process. This is not published. This is my opinion. Please come tell me I'm wrong at the coffee hour. I'd love to hear your thoughts on this. But at Mars, we do know photochemical escape is the main driver. Right now, it's the lead escape process. At Venus, it's going to be pickup ion for heavies. Genes is certainly going to be the most dominant escape process for the lighter constituents. At Earth, it's going to be that polar wind. And at Neptune and Jupiter, it's going to be that ion outflow when it does happen. But again, those are massive bodies. It is not easy to get out of there. So on that, I will just quickly conclude with, a lot of what we know about atmospheric escape has happened at smaller planets and moons. Ions are really a ubiquitous way in which things escape. When you have a heavy body, really something heavier than Mars, like something more massive than Mars, it gets hard to remove heavier constituents. So ion escape is really cool to study in this solar system, so we can start to apply it with our models in other stellar systems. And then, of course, we didn't talk a ton about hydrodynamic escape because in this solar system, we don't observe it. However, it's critical. And of course, as always, be kind to your host star. do your best to understand it, because we think that is one of the main drivers of escape. So thank you.
Okay, thanks very much, Shannon. Let's open the floor for questions for our solar system escape maven.
Yeah, that's Dave's contribution.
Okay.
Madeline Broom, UC Santa Cruz. And wonderful talk, by the way. It's an amazing review for a non-solar system person. I was curious, can ion escape have like a measurable effect on metal fractionation? So I mean, your overall metallicity of the planet.
You know, possibly. It depends again on the mass and the size of the planet, right? And so, and also how easily it can be ionized. And so I think that that can be the tricky piece. You know, I'd have to think harder. You know, it can, but what in this particular case, I would suggest an older stellar system would be where you'd want to start there, because that's going to take just more time to ionize things like I don't know, aluminum, or I'm trying to think of other metals that you would, I mean, depending on, really heavy things, again, are hard to get out. So I would say even at Earth, getting oxygen out starts getting hard. And so I will say the heavier the constituent, the harder it's going to be. But I would say, you know, very possible.
Okay.
Thank you very much. I'm Katie Bennett from Johns Hopkins. I just have like a couple of basic questions. So if you were to take all of our solar system planets and push them up against the sun, you know, in the way that all of our rocky exoplanets are, would all of a sudden, like, genes escape dominate over that ion escape? And likewise, like, when we're looking at these rocky atmospheres, would you still expect ion escape to dominate, assuming there is some kind of magnetic activity, or are they just too hot and
No, that's a
For people.
yeah. So for online, basically,
There's
if you
microphones in the ceiling, so they should be able to hear.
well, just the 10-second recap or 5-second recap is just if our solar system planets were orbiting much closer in, like the way we would expect to see rocky planets and many other stellar systems. Okay, so radiation falls off as 1 over r squared. So as you're coming in closer to the sun, it's really going to pick up. Yes, absolutely. Genes is definitely going to start kicking in much, much, much more exponentially so. That said, you know, and photochemistry to the same degree. That said, the solar or stellar winds, what we know about Earth, what we know about our star, right, is that the closer in you are, especially when you look at like a solar storm. So for those online, so there we go. You know, the closer you into, like, there's like this big wedge here. So if you're in the path of, like, because as it, you know, it dissipates as it propagates through the solar system, if you're chronically getting hit, both of them start to go up significantly. So it's a little hard to say, and it'll also depend on how active your star is. If you have a quieter host star, then I would say yes, genes will really start to take over very quickly. But if you have an active system, it's hard to say. I should also point out that when I've talked about like the dominant, I am talking about mass. The escape rate number, like genes escape at Mars is like 10 to the 26, and oxygen's, I'm going to call it like 10 to the 24, 10 to the 25. But when you look at how much mass is leaving the system, oxygen's going to take the cake there. So, yeah.
Okay.
Mateusz Schulik, Imperial College. You mentioned that for early Mars, sputtering would have been the dominant mass removal mechanism. But I guess in the exoplanet and planet formation community, we're much more married to thinking about early hydrodynamic escape. So what is the current thinking in the solar system community on when did hydroescape stop, and was it ever really important to remove the
well, it's all important, of course. So the reason we've talked about this many times. Okay, so we had, right, there's the primary atmosphere and the secondary atmosphere. The first, I'm going to say 500 million years, frankly, of every planet that forms in our solar system, but we'll use Mars, was cataclysmic in every way. You had like major impacts, right? You had much more volcanism, and that's when hydrodynamic escape operated. Hydrodynamic escape operates very quickly and very efficiently and like aggressively. So we've talked about like 10 to the 5, 10 to the 6 years to wipe out, and that's when it becomes We go from energy limited to source limited. You can't, there's nothing else to wipe out. But again, for those that study everything about an atmosphere from like above and below, there's all this volcanism taking place. There's all this outgassing taking place. So now a secondary atmosphere is forming. And so whenever you're looking at really young systems, that's when you're going to see most likely a lot of that hydrodynamic escape, in particular with rocky planets. But, you know, at larger planets, that's sort of a different beast. But eventually when that primary atmosphere has been swept away, and I'm glossing over a lot here, that secondary atmosphere, as the system ages and you get more outgassing, that's when you start to see more of what we'll call like these kinetic escape processes that we see in today's solar system. So hydrodynamic escape just isn't operating, A, because our sun has calmed down, it's more middle-aged, right? So, and then also just the radiation, same thing. So that's sort of the Cliff's Notes on that.
Okay, and just a reminder for the people online, it'd be okay for you to ask a question if you would like, no pressure. And I'm looking for hands raised on the Zoom and also questions typed into the chat. So I'm monitoring that just in case.
One question, can I have one question?
Yeah, go right ahead.
Hi, this is Bahman. Thank you for your great talk. I'm wondering, how did you get the plot at the middle, the left one, conclusion, at the middle, the left panel? I didn't get how did you create this plot? That's data, I think that's simulation, right?
Yeah, how were the 3 plots in the middle created? Is that simulation or those observations?
No, everything you're saying here is an observation on this last conclusion chart. So this is Mars, this is Venus Express data, and then this is Earth, and then up here, this is all Mars, but this is just looking at that photochemical, and this is basically the hydrogen, the oxygen, the carbon corona, and so effectively some of that's bound, some of that's escaping. Then on the bottom panel, this is to some degree a little bit of a compilation of what's going to be some of our like stereographic imagery, but some of it might, no, those are ours.
So all observations.
Those are all observations, yeah, which is pretty cool that we're able to map these things. And again, also a reminder, go NASA science, you have to keep these things in orbit for a long time to do good work.
Okay, any last quick questions? Okay, Evgenia, no, do it, go for it.
So what is their plan to observe the Earth? Are there any mission concepts that you know about?
Yeah, there have been. Do you want to comment?
Go first, and then I can fill in if you want.
There certainly have been concepts, and concepts that have certainly gone just beyond the pre-phase A stuff. They just haven't been selected yet, to my knowledge.
Yeah, I can mention a couple of things. So Carruthers just launched to observe Earth's geocorona, and so it's geocoronal observations, but ESCAPE will be a byproduct of those observations. Yeah. Tracers is exploring acceleration processes in the magnetosphere, so ESCAPE will be a byproduct. And then, as Shannon said, lots of things have been proposed over the years and keep getting very close.
Nothing dedicated. Like the Artemis Themis missions here and MMS have also done incredible work. And really, this is where you start to see spacecraft in like a series. Having more than one vantage point is critical to do that at Earth. But we really haven't. That's what GDC would have done. So GDC would be game changing in doing that. GDC would be far away the most dedicated observatory to do that. But right now it's stood down. So.
And GDC is Geodynamics Constellation, the heliophysics flagship that almost was.
Flagship, and it's in development. It was selected and well into.
Okay, with that, let's thank Shannon one more time.
Microphone.
I'll let you get it in play mode. Okay.
Okay, you're assuming I know how to get it in play mode. Let's see.
Oh yeah, there you go.
This one.
Okay, so the next speaker is Mike Chaffin, and the slides I think are coming up. Oh, they're coming up on the wrong screen.
Automatically advancing, so
they're coming up on the wrong screen too. We're getting a lovely forest view.
That's fun.
If you just drag it in.
I'm trying.
Left. There you go.
Okay.
Okay, so Mike's presentation is titled Venus, Earth, and Mars, Laboratories for Understanding Terrestrial Planet Water Escape.
Great. Okay, so Shannon gave a great introduction about why we care about this for solar system planets. Planetary water loss, H and O loss from the upper atmosphere to space can result in desiccation and oxidation. These are two images from Mars, one of an ancient delta flowing into a crater that shows that water used to flow over the surface, but it now no longer does. And one, a drill hole from the Curiosity rover on the surface, showing that the outside of the rocks on the surface of Mars are rusted, but the inside is not. So some of the oxygen that might have escaped instead went into the interior on Mars. We need to understand hydrogen loss, and we need to understand the differential loss of hydrogen and oxygen in order to understand how these processes might limit planetary habitability. Shannon gave you an introduction to Mars. There's 6 millibar of atmosphere on Mars. We know that Mars has experienced substantial volatile escape over its history from the isotopes. Isotopes of carbon and CO2, of oxygen, of nitrogen, of argon and other noble gases, and of D to H. In particular, the D to H ratio on Mars is about 5.5 times the Earth in the atmosphere today. We don't know the D to H ratio deep in the polar caps or in any subsurface water, but that ratio alone in the atmosphere tells us that substantial escape must have occurred. And one thing I want to mention that's going to come back later is that Mars experiences these planet-scale weather events every several Mars years. It's still not understood why a dust storm occurs in any individual Mars year, but they seem to happen every several Mars years, and they can envelop the entire planet with, as we'll see, impacts on escape to space. Okay, Shannon mentioned Jean's escape and showed this image of the corona of Mars that was assembled from MAVEN's insertion orbit around Mars. Jean's escape is the predominant mechanism by which hydrogen has left the Martian atmosphere to space over its history, and Mars is maybe the simplest planet to consider when it comes to what has removed hydrogen and therefore water from the system over time. So Jean's escape is once again this high energy escape from the tail of a thermal velocity distribution. On Mars, we constrain this with usually spatially resolved measurements of hydrogen, lime, and alpha, as opposed to the spectrally resolved measurements that are point source measurements that you get for exoplanets. The radiative transfer that we do to constrain this loss is optically thick, though, so there's some additional details because we're looking at the planet in scattered light rather than in extincted light. Okay, we think about escape to space via Jean's escape with this escape parameter. So I don't know if this counts as the Jean's escape equation, but it's definitely the Jean's escape parameter for the purposes of your bingo card. And this Jean's parameter is the ratio of the escape velocity to the thermal velocity squared. It's kind of counterintuitive, but the larger the lambda is, the more tightly bound the atmosphere is, and the less escape you get. So lambda is like the strength of the binding of the hydrogen to the planet. And if lambda gets down to around 2 to 3, fluid affects matter and escape becomes hydrodynamic. This description no longer applies. So you can see a range of different temperatures for velocity distributions. Typical temperatures for Mars and Venus are around 200 Kelvin. Typical temperatures for the Earth are around 1,000 Kelvin. And that leads to this sort of chart of whether we care about Jean's escape on the various planets in our solar system, terrestrial planets with atmospheres anyway. So the Earth's thermosphere is hot, but the thermosphere of Mars and Venus are cold. We got a great overview yesterday about why this happens. It's conduction of heat down in the O2 N2 atmosphere of Earth to a point where it can be radiated by CO2 that causes this high temperature on the Earth. At Mars and Venus, you don't have to worry about this. You can just radiate more or less directly. Earth and Venus have high gravity. Mars has low gravity. And as a result, you can get substantial genes escape from Mars and the Earth. On the Earth, the high gravity is counterbalanced by a much higher thermospheric temperature. But on Venus, genes escape is insignificant. So if all we had to think about were genes escape, then Venus would still have all of its original water. Okay, but genes escape isn't the only process that operates at Earth. Even though it's significant at Earth, there are other processes. Shannon talked about several of them. For hydrogen loss from the Earth, the two dominant processes today are genes escape and plasmasphere charge exchange. So this plasmasphere charge exchange occurs when you get hot ions in the Earth's plasmasphere that are on banana orbits, bound banana orbits, bouncing back and forth between the poles. Those ions are heated by all of the magical electric and magnetic field processes that can operate on ions and not on neutrals to higher temperatures than the neutral hydrogen in the Earth's corona. But because there's substantial neutral hydrogen surrounding the Earth out to large distances, you can occasionally get charge exchange, resonant charge exchange between these protons and coronal hydrogen atoms, which results in very fast energetic neutral atoms, or ENAs. And this great overview paper by Pratik Joshi from 2019 shows using radiative transfer observations of Lyman alpha that about 85% of Earth's hydrogen escape at solar max occurs via genes loss, with the balance made up by plasmasphere charge exchange. And this swaps back and forth over the course of the solar cycle. At solar min, the thermosphere is cooler. There's less escape to space via genes escape, but these non-thermal processes pick up the slack, and the overall rate of H escape is approximately constant over the solar cycle. How can that be? There's so much more energy being input into the system at solar maximum than at solar minimum. And the way that this happens is that the loss process is not energy limited. It's diffusion limited or supply limited from lower down. Shannon showed a great picture of a polar bear. If you like, you can imagine there's a polar bear jumping into this pool on this slide. But I like to think of energy limited escape as like splashing stuff out of an abundant source region, whereas diffusion limited escape, the escape process itself is very efficient. It's supply to that escape region that is difficult, right? So the storm drain is going to remove all the water that gets there. The hard part is getting the water to the storm drain. So if you want an overview, an analytical or mathematical overview of diffusion limited escape, you can go to this paper by Hunton in 1973, which was recently updated by Roger Yale in 2024. The bottom line is for terrestrial planet hydrogen, diffusion limits the ability of hydrogen to make it to the upper atmosphere where it can then subsequently escape. And on all of the terrestrial planets, this diffusion limited escape limits the loss rate of H, but not deuterium or heavier species. Okay, so this diffusion limit applies either at the base of the thermosphere or in the region of the cold trap. This is a cartoon from Earth showing that you can either prevent hydrogen from reaching the escape region in the base of the thermosphere or in the lower atmosphere by preventing water from getting into the upper atmosphere. On Earth, it's methane that's the non-condensable species that's able to get past the cold trap and into the upper atmosphere carrying H that it might eventually escape to space. And we should really be thinking of the escape region as a reservoir, where supply into that reservoir is the ultimate limit on how much can be removed from the top. And if escape is efficient, it's really the supply processes that we have to care about. On Mars, those supply processes were thought for a long time to be very similar to the Earth, that there was a cold trap that was very strong in the lower atmosphere, and that it was really the diffusion of molecular hydrogen into the upper atmosphere, into the base of the thermosphere that controlled escape. But we now know that those dust storms that I talked about earlier are actually capable of lofting significant amounts of water into the middle atmosphere of Mars. And so what we have on Mars today is not really a diffusion limited scenario, although diffusion is important. It's a supply limited scenario where it's the ability of water to access the middle atmosphere that limits the ability of water to be removed from the system. On Venus, the situation is different. And Venus today has virtually no water. 3 centimeters is a global equivalent layer spread evenly around the planet, as compared to an initial inventory of maybe 3 kilometers, 300 bars of steam. And the D to H ratio is enhanced dramatically. I don't have time to talk about the D to H fractionation, but we can talk a little bit about why the water abundance is so low and whether Venus might have ever had oceans. So we think the best idea that anyone's been able to come up with to explain how you lose an ocean of water from Venus is that there was some early period of hydrodynamic escape that shut down at some point in the past, probably more than 500 million years ago, which is the approximate age of the surface. This escape began in a runaway greenhouse with all of the atmosphere, with all of the water on the planet in a steam atmosphere. That's either the original steam atmosphere that was outgassed from the planet or a later steam atmosphere that was created via a runaway greenhouse scenario. When you put all of the water into the atmosphere, it can dissociate into hydrogen. And if you have more than about 1% of hydrogen in the upper atmosphere, in the thermosphere, you have very inefficient cooling, and you can drive outflow from the upper atmosphere to space. Da Vinci's noble gas measurements, particularly of the 9 stable xenon isotopes, will help to constrain how this process worked. Thanks, Dave. These xenon measurements are really diagnostic for distinguishing between sources of water and other volatiles to the planet and various escape processes, including hydrodynamic escape. But importantly, hydrodynamic escape is a self-limiting process for a planet like Venus, because the escape results from a hydrogen-dominated thermosphere. As you remove water from the system, eventually you no longer have enough hydrogen for it to dominate the thermosphere. And if it takes about 1% of the atmosphere to have a hydrogen-dominated thermosphere or to have hydrodynamic escape occurring in the thermosphere, then we can reason from the 90-bar atmosphere today that hydrodynamic escape should shut down with about 10 meters of water left in the atmosphere, about 1 bar. But that's way greater than the 3 centimeters that are left in the atmosphere today, so we need non-thermal loss processes to explain the rest of the loss. And there's been a lot of work done on this. These non-thermal processes include the kind of resonant charge exchange that we talked about for the Earth, but this time operating in a system where there is no global magnetosphere. Impact from hot oxygen. Shannon talked about this photochemically produced hot oxygen that's bound to the Venus system. That oxygen doesn't escape, but it can slam into a hydrogen on its bound orbit and knock that hydrogen out into space. And then ion loss processes, which we really don't understand at Venus. There's enough energy in the ionosphere to power a lot of escape, but very little escape observed down tail. And added to this are processes that are photochemical and remove hydrogen from the atmosphere via photochemical reactions. So Aaron Kanji and I published a study on this in Nature last year. The title that we put on this cover that was not selected is my submission for pun, Dave, so take a note. And by doing this one-dimensional photochemical modeling, we were able to show that this HCO plus dissociative recombination loss is actually the most important loss mechanism from Venus to space today. So if you want to understand planetary volatile loss, you need to understand planetary ionospheres. And the way that we do that in the solar system is with in situ observations. So we're going to have to get creative in order to do that for exoplanets. I think for the purposes of having questions, I'm just going to skip to the conclusion slide here. I have some more details about this Venus work that we did, including, answering this question of where the oxygen went. But for the purposes of fulfilling the mandate of the talk, this is the conclusion slide, which shows you the rates, the dominant mechanism, and some of the unknowns. Thank you.
All right, thanks very much, Mike. I hope that there are at least some questions for Mike.
I'd actually be interested in hearing your thoughts on where the oxygen went.
Okay, the very short answer is we don't know, and it seems really hard to.
I was afraid you were going to say that.
Right, almost mass.
Can you elaborate?
The initial 3 kilometers of water is in the oxygen, right, which means that if you remove all the hydrogen and leave all the oxygen behind, there should be 300 bars of oxygen on Venus right now, and there's no O2 or atomic O in the atmosphere. So, you either have to remove it to space, which is really hard because there are no neutral loss mechanisms and ion loss rates are low, or you have to bury it in the interior. And of course, there's enough room in the interior to bury it because that's where it came from originally. The question is, can you do it kinetically? And that seems very difficult, and I don't think we really understand the kinetics of how that burial might work.
Thank you.
So Mike, one question that, by the way, is Leo dos Santos from STScI. One question that I get very often from other people, other exoplanet people, when I go to a conference, especially like an HWO conference, is can we observe the Earth's Earth-like hydrogen exosphere, independent of the challenge of a UV coronagraph? But can we observe an Earth-like hydrogen exosphere in direct imaging or through scattered photons? And
Yeah.
can we use a model that you use for Mars, for instance, to apply that to exoplanets?
Yes, in principle, one could. The interstellar absorption is going to be hard.
Yeah.
But I was thinking about this yesterday. It seems to me that if you have a planet like the Earth, which has an orbital velocity of tens of kilometers per second, that if you can block out enough of the starlight, you should be able to make observations in blue shift and in red shift as that planet is moving around its star and get something for the Lyman alpha brightness of the planet itself. Interpreting it is going to be really hard, but you could make a measurement.
Okay, and you can catch Mike at the break if you have more questions. With that, let's thank him one more time. Oh, that's what's going on. Okay, and the next speaker is Leonardos Gkouvelis. I hope I did that okay.
Thank you.
We practiced once before, but I think I screwed it up ultimately.
No, it was.
And titled is Stability of Secondary Atmospheres and Observational Manifestations. Take it away.
So hi everyone, I'm Leo. I'm working at the University of Munich. I'm a staff scientist. So when we talk about the characterization of rocky exoplanets, in my mind, the ideal characterization would be to answer these three fundamental questions. The first, simple, is does it actually have an atmosphere? And this is actually very relevant to the sample that we know today because they live in a very closed orbits and in very, very harsh environments. The second, talking about habitability, whatever habitability might mean for you, each one of you at this time, if you want to say something to assess it, you need to constrain some physical parameters, which of course at this moment is like a fantasy. And the last one, when we want to, in the future, we want to talk about biosignatures, and if we want to make bold claims about detecting biosignatures, I think we first need to understand pretty well what is the capacity of the planet in producing abiotic signatures, right? What is the physics that goes on there? Okay, so the two last questions, of course, we are very far away from it. It's like a fantasy right now, but where the community is right now, it's on the first one. This is very well reflected in many papers right now in the literature. Many of them Nature, Natural Astronomy, etc., which is an indicator how hot is this topic. So in this plot here, what I'm showing you is here the secondary eclipse depth as a function of wavelength. The observational data is only one this point, which is okay for me. It's fantastic. At this CO2 very strong absorbing band at 15 microns. And what people are trying to do is, okay, I have this observation, this one point here, which I think is the DT program from James Webb. And then I try to match it with some scenarios. For example, here there are some scenarios which are atmospheric, like with secondary atmospheres, and some scenarios which are like how a bare rock should look like in our telescope. Okay, you see obviously that here it's kind of degenerate. So with one point, people have realized that with one photometric point, you cannot say much. So they have recently started to observe in 2 points, 2 photometric points to say something extra. Unfortunately, this is also degenerate. So the question is, okay, how can we robustly say if a given system has an atmosphere or it's actually a bare rock and the atmosphere vanished early or sometime in its lifetime? So the idea here is to explore, to be able to predict with modeling or theory, what is the capacity of a given system in producing, say, signatures as a bare rock, and we can try to explore a big parameter space, or with atmospheric signatures, and I can do the same. So what I wanted to do is I want to touch both a bit today, briefly, of course, I don't have time to do much, some challenges that we have to overcome in order to be able to solve this problem. For example, for the bare rocks, of course, we don't know the composition of the material of the surface of a given exoplanet, so what we are doing is trying to pick a guess. Say, for example, if this exoplanet is ultramafic, how it should look like to our telescope. You see here that it's actually, they have spectral signatures, so it's complicated to separate them from an atmospheric signature. But in order to model them, to model those spectra, among other things, I need some specific parameters of the material, which are basically those four. 1 second. So in order to model this, I need these two functions, which one is the reflectance, which I have to measure in the laboratory. The other one is something which is called opposition surge, and is brightness enhancement and are at low, when approaching at low phase angles. So the problem is that laboratory measurements exist. For example, I'm showing you here some examples in wavelength, which are very dense in the wavelength range. This is the reflectance, which is this function here. They are very well measured as a function of wavelength, but they are only one geometric measurement, which means that the detector has one specific angle and then measures at many wavelengths. And you understand that if I have only one measurement per wavelength in geometry, I cannot constrain 4 parameters here. So it's degenerate, right? It's impossible. So what the state of the art in exoplanet is, we completely forget the opposition surge, mainly. We make some crude assumption on this B parameter, which is the asymmetry function when the photons come. This is an indicator of what is the fraction of photons, which direction they are going to get scattered. And this is the single scattering albedo, which tells you what is the fraction of photons that will get absorbed by the material and what is the fraction that will get scattered. So we actually kind of scale this factor, and then we create the spectra I was showing you here, which, so you understand that it's kind of a big approximation right now. So how can we overcome this problem? Is I have dig up in the literature, and there are actually proper measurements which are very dense in the phase angle space. This is an Apollo sample from the moon, from dust from the moon, which they have measured the reflectance in the laboratory actually pretty well. But the problem here is that in the wavelength coverage, it's very poor. There are only 4 photometric bands. And once I use these measurements, I can immediately constrain the needed parameters I need to model bare rocks. Okay, that's one thing. But these measurements, someone has to do them in the future. If in long term we want to characterize surfaces on rocky exoplanets, we cannot avoid it. I think we have to imagine this the same as is the databases of opacities for the characterization of the atmospheres, but they don't exist right now. So going out to the atmospheres, the question here is now, for a given planet, what is the capacity of that planet in producing secondary atmospheres, and that atmospheres to actually be stable in time, and they can be in long term survive. This is more challenging, as you all know here. We have 2 communities here. We have already talked about the upper boundary of the atmosphere, and I guess tomorrow we are going to talk about the lower boundary, the outgassing, the generation of the atmosphere. And then the atmospheric processes here are complex, but I think we can dominate it. But the numerical challenge here is to couple, to do the climate modeling here, but having a good treatment of both the interaction with space environment, but also with the lower boundary, with the interactions with the interior. So we did the first try on this. We published this paper last summer. So what we took is a very detailed climate model where we treat both the lower boundary with outgassing and the upper boundary with escape regimes. So with this, we can take a given system and do a pretty well parameter space exploration to check the secondary atmospheres that you can produce, but also how they can, if they can survive in time. I don't have time to say technical details. You can go to the paper if you want. Just jump to some results here. We choose this specific planet, which is about the mass of the Earth, for reasons that you can check on the paper. And what I'm showing you here is the mean molecular weight in color, the mean molecular weight of the atmosphere at the RxUV level, which we said yesterday. It's the layer of the atmosphere where the XUV flux optical depth is about unity. Here on the x-axis is the redox state of the interior of the planet, of the melt. Right, for example, here on the left is the more reducing, so you can produce secondary atmospheres which look like an embryo atmosphere, H2 dominated atmospheres. And here on the right is more oxidizing carbon-bearing species, oxygen, etc. And here is the surface pressure of the atmosphere. So what we find is that to stabilize the atmosphere, so here it's the hydrodynamic escape regime, and here the atmosphere, the thermosphere stabilizes. So the difference you see here is about 3 kilos per second in mass loss, while here it's many orders of magnitude. So even with the back of the envelope calculation here, and having an approximation of the lifetime of the planet here, you can find out that whatever the initial volatile budget of the planet, if it was in this regime here, it will saturate at this time. So you will actually stay in a dry, bare rock. Okay, so having explored this big parameter space, I can, now I'm just showing you a small subsample of those synthetic spectra. We can now go and explore observational strategies of how we can distinguish between one and the other. For example, I'm showing you here, I can select the 15 micron, which James Webb actually right now has this program. We can plot this 15 micron here. In one side, I have the bare rocks. And the other side, I have various atmospheric scenarios as a function of their interior redox state on the melt. I don't include even errors here. It's obvious that this is degenerate. You cannot separate with one band. It's impossible. Here in rings, I have the atmospheres which actually can survive in the long run, right? But still, it's degenerate. Now, if you go with 2 photometric bands, it's still degenerate. You cannot say much, and you can go in the paper for that. And we are not the only ones to show this. There is another paper. So what we predict and what we propose is that if you construct a color diagram, famous for astronomers, you can actually distinguish between bare rocks because they cluster in one side of the diagram, and the stable surviving atmospheres cluster on the other side. I have another more busy plot in my paper which includes clouds and hazes, and it's still nice like this. And that's all for me. Questions?
Great. Questions for Leonardos before we let him escape?
Just to follow up on this part going through scientific, do you have any sense of the feasibility of these color measurements with JWST?
Yeah, so
JWST bands, is that
yes.
Right? Okay.
So those those filters exist right now on James Webb, and I can show you the other plot. It's this one. It's more busy, but the thing is, I include here a synthetic observation, let's say. Unfortunately for this planet, at 1 sigma detection, It has to be around here. So all of this shadow region is secondary atmospheres, which survive. These are the bedrocks. And these dusties are like either clouds or hazes at big parameter space, so possibilities. But only this shadow region is if this planet has an atmosphere. If you bring this point, let's say, to the left, it's below 1 sigma, so you cannot see. But if you bring it to the right, it's more than 1 sigma. So 1 sigma is about here. So in theory, it's feasible. You can observe this. Now, how many times you have to, orbits you have to observe? I don't know, because I'm not an observer, but I've done this.
Hello, Brandon Coy from Chicago. I was wondering so the Barrock cases look a lot like the reducing atmospheres with just one filter. But I was wondering kind of what assumptions you were making about how efficient like a 10 bar sort of reducing atmosphere would be at redistributing heat and cooling the day side. Like, are you just assuming?
Okay, yeah, that's a good question. So I'm solving the heat redistribution, okay. so self-consistently. So this is included too. So for technical details, if you check the paper, it's everything there. Just one thing to mention here, that this is axis here, it's for the specific system. So every time, if the planet is more bright, you can go more than 3 to, I don't know, depends how many sigma.
One last quick one.
Hi, Trent Thomas from the University of Washington. Could you speak a little bit more about the how you're calculating the volatile fluxes at the low boundary condition from the?
Yeah, I guess there are going to be extensive lectures tomorrow about this, but essentially it's like you take the system of the interior and the atmosphere as a let's say closed system in equilibrium, and you solve to minimize the Gibbs free energy. So you partition between melt and gas. So you need only 4 parameters as inputs. So then you partition the interior volatiles in the melt and in the gas, but then you have to solve in the gas all the kinetics, radiative transfer, etc.
Okay, let's thank Leonardo. Great, and the final presentation of this part of the session is given by Rahul Arora, and the title is Thin H2-Dominated Atmospheres as a Diagnostic of Exovolcanism.
Thank you. I'm audible, right? Okay. Good morning, everyone. My name is Rahul Arora. I am a third-year graduate student at University of Arizona, and today I'll be talking about how we can use hydrogen as a diagnostic for exovolcanism. So most of the rocky bodies in our solar system has shown evidence of active or dormant volcanism. So a natural question arises, can there be volcanism outside the solar system on exoplanets? But before I actually get into answering the question, can we or not, I'll just go through a bit of why do we need to study exovolcanism at all. So primarily, it helps us understand the planetary interior. It gives us a view into the interior composition of the planet, which is not an observable quantity, through the atmosphere, which is an observable quantity, which in turn can help us understand where and how the planet formed and how has it evolved through time, as well as what kind of exotic compositions can there be in these exoplanets, which we do not find in the solar system. On the other hand, it also has astrobiological relevance. It acts as a habitability indicator and helps us understand false positive biosignatures. So our key idea is thin H2-dominated atmospheres on tidally heated, closed-in rocky exoplanets will serve as a diagnostic for present and active volcanism. The biggest hurdle that we face in forming these thin H2-dominated atmospheres is the escape. These planets are so close into their host stars, they are highly irradiated by their exuvial fluxes, and most of the H2 atmosphere that should be there in these on these exoplanets would escape away into the space. And previous studies have shown that Earth-like outgassing cannot outpace this escape and form an H2-dominated atmosphere. But what about tidally heated planets which have high eccentricity? So to basically get an intuition, this is a plot where a lot of exoplanets have been plotted. On the y-axis is the tidal heating, and on the x-axis is the equilibrium temperature of the planets compared to Io. And what we find is there are so many existing exoplanets which have orders higher tidal heating compared to Io, which has evidence for active volcanism. So can these planets be something like super Ios or not? So what we get from these planets' planetary properties is just the amount of heat that they get. How do we convert this into what we actually care about is the flux of hydrogen into the atmosphere. We linearly scale the flux of hydrogen using the heat in this exoplanets and the heating that we see on Earth. And then we calculate the flux of the hydrogen using this heating parameter and how much of hydrogen would be outgassed compared to other gases, basically the speciation of different molecules through the outgassing part. So we follow a particular methodology where we try to understand how these planets can form, what interior properties would help in formation of these planets, and are they detectable or not. So we start with an open source outgassing code which I built to calculate how much and what molecules would be outgassed under certain interior conditions, coupled with photochemical and radiative transfer codes to understand if they're detectable or not. On this figure in the bottom left, I show a case study of a particular planet L9859T, which is tentatively expected to have volcanism on it. What we show is that H2 dominated atmospheres, which is shown in the red, it's more like a 10 atmospheric unit mean molecular weight atmosphere, which is the observed mean molecular weight for the planet, is way more detectable than an N2 based atmosphere, just like we see on Earth. So where do we exactly find these planets, and how do we compare the outgassing and the escape on these planets? So what we find is that the tidal heating of these planets is basically permitted by two different terms here. One is the distance from the host star, the A, and the second is eccentricity. So higher the eccentricity of these planets, there's more tidal heating, and the closer it is to the star, there's more tidal heating. But there's a particular dependence of how the tidal heating changes with the distance of the host star. Whereas there is a totally different dependence upon the distance from the host star for the escape. What we find is that the escape increases slowly when the planet moves towards the star, and the tidal heating increases more steeply. So counterintuitively, we would find these hydrogen-dominated atmospheres closer to the star rather than farther from the star. And an example of that is shown in this figure for two planets L9859b and D, which both lie in the outgassing zone for themselves. So the dashed line shows how, if these planets were at different semi-major axes, how their tidal heating or outgassing flux would change in the dashed line, and how their escape would change in the solid line. So now we have found that some planets can have more tidal heating than their escape, but is tidal heating enough to show that they can have thin H2 dominated atmospheres? And the answer is no. So there are a few more parameters that these planets need to have for them to form thin H2 dominated atmosphere. Thing number one, volatile inventory. So if the planet does not have enough hydrogen in it to outgas and form this thin H2 dominated atmosphere, it will just lose all of its volatile inventory within a few mega years. So these planets need to have enough hydrogen in the melt so that they can outgas for geologically long time. And here we basically characterize geologically long time by the time scale of 1 gigayear. On the figure on the right, we show that in two different regimes of volatile inventories, water poor shown by the dashed line and water rich conditions shown by the solid lines, we find that there are few planets in this particular set of planets that we have chosen that can sustain an hydrogen dominant outgassing for a geologically long time, even for 5 gigayears or more. But none of these planets can host this hydrogen outgassing for geologically long times under water poor conditions. So water rich mantle is an important condition. Second would be how these different molecules are being outgassed, how much of these molecules are being outgassed. So to form an H2 dominated atmosphere, we need an H2 dominant outgassing, which is decided by the redox state of the melt. The outgassing can be H2O based, CO2 based, or H2 based. And to get an H2 based outgassing, we need the melt to be highly reducing. To show, basically this plot shows that we ran a set of 10,000 models ranging a whole volatile inventory cases and redox melt states, which are being shown in this figure. Each block shows the density of number of models lying in that particular hydrogen outgassing as well as redox states. And what we find is as we go more and more reducing in the melt, the hydrogen outgassing keeps increasing. This is also important because other than hydrogen, heavier molecules can also outgas into the atmosphere, which would not lead to a low mean molecular weight atmosphere. And to suppress specifically sulfur and carbon, we need reducing melts. Carbon mostly stores as graphite inside the melt under highly reducing conditions, and sulfur also dissolves as sulfide. So as an example, for L9859D, a reducing melt, more reducing than FMQ minus 4.5 would be enough to form an H2 dominated atmosphere. So if you're actually able to find and observe such a planet with a thin H2 dominated atmosphere, how do we exactly know it's volcanically generated and not just a leftover part of the primordial atmosphere? And to actually separate these two conditions, we use the lifetime of the existing atmosphere on these planets, where we calculate whether the lifetime under the current escape of the planet is less or more than 100 mega years. So if it is more than 100 mega years, the planet atmosphere is quite thick, and it is more likely to be primordial. But if it's less than 100 mega years, it's highly unlikely that we're observing the planet's atmosphere in such a short time, where it would have been lost within a few mega years. And it's more likely to be secondary. And this is the reason that throughout the talk, I have been focusing on thin H2 dominated atmospheres and not just H2 dominated atmospheres. So we propose a 3-step procedure to find these planets. Step 1 would be to find potential outgassing zone candidates using their nominal mass radius and eccentricity constraints. Step number 2 would be to confirm the candidacy of these planets by having more precise eccentricity constraints on these planets, or trying to find planets in a multi-planet system where they're under mean motion resonance. And step number 3 would be to measure a low precision JWST spectra, where we can constrain their mean molecular weight to understand whether it's low mean molecular weight or high mean molecular weight atmosphere. Before I actually go to the conclusions, I would like to acknowledge Gkouvelis Foundation and the National Science Foundation for the support. And these are my conclusions. I would like to highlight 2 of them. That is, if we are actually able to detect these atmospheres, we can constrain the interior properties of the planets, specifically the redox state as well as the volatile compositions. And even non-detections now can be used to infer something, maybe broad ranges of constraints, but yes, it can be used to provide some constraints for the interior properties. Thank you.
Okay, thank you, Rahul. Are there questions for Rahul? It could be about his primary topic or any secondary topic that you come up with. I'm regretting this just as much as you are.
You're committed to the bit.
Yeah, you know, once you do it for one, you got to do it for everybody. Okay. Great.
Yeah, Michael Zhang, University of Chicago. Yeah, you talked about how you can tell whether the atmosphere is hydrogen dominated. How can you tell whether it's thin?
So that part is more like if we can observe the density mass radius constraints of the planet, like have finer and preciser constraints on that, we can actually constrain what's the mass of the atmosphere on the planets using that. And if we have the XUV constraints of how much the planet is losing, we can put up a constraint on the lifetime of the planet's atmosphere, basically.
Thanks for the talk. I think it's really very college. The hydrogen you outgas, does it have a feedback effect on the lower atmosphere, particularly the greenhouse effect in the lower atmosphere? Because I think you had a significant amount of hydrogen that you produce. And I think it was argued in the past that via collision-induced absorption, that can be a potential, powerful greenhouse gas.
So the feedback effect would mostly be upon the surface pressure. It's obviously going to affect the temperature as well, but I would say the major feedback that would control further outgassing as the evolution of time would be the surface pressure and not the temperature, because surface pressure does dictate how much of outgassing would be happening.
But does the temperature not go into that? Really affects.
It would. It would have, like with the greenhouse effect, it would have the radiative effects. Sure.
Okay, and I'll do one question here as well, and it's more about the setup. In the Jupiter Io system, a key characteristic of that system that makes Io so strongly tidally heated are the orbital resonances with the exterior moons. And so the setup here, is that assuming similar orbital resonances to keep things eccentric, or more favorable mass ratios between the star and the planet that allow things to stay eccentric for longer? Is that sort of the thinking here?
It can be both. Either we have a confirmed detection of high eccentricity on the planet, or we would be favoring mean motion resonance planets. And the example that I showed with the L9859 system is a mean motion resonance system.
Perfect. Great. Thanks. Okay, let's thank Rahul one more time. Are there any announcements before we go to coffee break? Back at 11:15 on time? Yes, back at 11:15.